On average, 10,000 muons hit every square meter of the Earth's surface every second. These muons, referred to as secondary muons, are created about 4,700 meters above the surface of the Earth by cosmic rays colliding with the atmosphere. A muon is kind of like an electron. It has the same charge and spin, but it has about 207 times as much mass as an electron. The muon also differs from an electron with a very small mean lifetime of 2.2 microseconds, that is 2.2 millionths of a second. But wait, doesn't the laws of physics prevent a 4,700 meter journey in 2.2 millionths of a second? Using classical Newtonian physics, namely average velocity is equal to distance over time, the muon will move way faster than light, 7.12 times faster in fact. We all know that this is impossible since the object has mass and anything with mass has to travel at a velocity less than the speed of light. Several experiments have been made and the muon's velocity has been determined to be 99.97% of the speed of light. But then how can a muon make this seemingly impossible journey? The man with the solution? Albert Einstein. In 1905, Einstein revolutionized the world of physics with his paper entitled On Electrodynamics of Moving Bodies, which would later be called the theory of special relativity. He did so by deriving the Lorentz transformation under the assumption that the equations describing the laws of physics have the same form in all valid frames of reference, that the speed of light is constant, and by abandoning the mechanical ether preceding the theory. Most of the mathematics of the paper was derived 13 years earlier in 1892 by a Dutch physicist Hendrik Lorentz. The complete explanation is two-sided, like a coin. On one side we have the muon's frame of reference or viewport, and on the other side we have the Earth's reference frame. In the Earth's frame of reference, that's where the Earth stays at rest and everything else, including the muon, moves relative to the Earth at a speed v. This is where there's a fixed distance between the atmosphere, where the secondary muons are created, and the surface of the Earth, namely 4,700 meters. This is where the concept of time dilation comes in. Time dilation tells us the relationship between the proper time and the time as recorded by the muon. Delta t prime equals delta t over gamma to get mathematical. Plugging the muon's mean lifetime into this equation, we discover that relativistic time is about 89.8 microseconds, which is more than enough time to travel those 4,700 meters to the surface of the Earth. In the muon's frame of reference, that's where the muon stays at rest, but everything around the muon moves relative to it at velocity v. This is where the effect of length contraction comes in, meaning that when a particle travels close to the speed of light, the space traveling toward the muon gets contracted. But for this to happen, the Earth has to be stretched mostly orthogonally to the velocity of the Earth. By using Lorentz's formula, L is equal to L naught over gamma, where L naught is the proper length, namely 4,700 meters, we can see how long the muon has to travel due to its relativistic velocity. Plugging in the velocity and proper length, we discover that the length the muon actually has to travel is about a mere 115 meters. And it is these two relativistic effects that make it possible for muons to be detected at the surface of the Earth, even in deep caves 700 meters below the surface. And it is yet another proof of special relativity, so thanks Lorentz for thinking of your cute mathematical trick, and thank you Einstein for putting this cute mathematical trick all together, with some help to form what we know today as the theory of special relativity. Thank you for watching this video on why muons reach the surface of the Earth. I'm interested in hearing what you think. Do you have any suggestions or comments? Please comment in the comment section below. Please leave a like if you enjoyed the video and feel free to share this video with your friends and family. So thanks for watching.